Okay, boys and girls. Okay, before I forget, for the next week tuition, I will not be able to conduct our tuition. Is because I have to attend and involve in the school leadership camp. Have to overnight at school on Friday, so I will not be able to conduct. So as a replacement, we need to replacement class, right? Actually, I already checked. October we got 5 Fridays. So actually our lesson will be like 1 month is 4 lessons. So supposedly we will take 1 week to rest, okay, for the next month. But since this September, we will miss 1 lesson. So for the October, the 5 Friday, okay, we will have a continuous learning for our lessons for the throughout the October lah. Okay. Is that clear? Later on this message I will paste again in the group lah. Okay, I want to inform you guys that next week everybody relax, okay? But then on October we will having 5 Friday. We will have continue learning, okay? Is it okay? If clear, then give me some reaction before we start our lesson. Thank you. Okay, like boys and girls, last lesson actually we already finished, okay? Then after that, the few questions I haven't touched, and then I ask you do it by yourself. The model answer I already share in the group. Okay, the model answer I already share in the group. And then the self-practice one, please do it and check it out. Okay. So today we're entering chapter 6, deformations of solid. Okay, what is the meanings of deformations? Deform meanings that change shape. Okay, what will change shape? When we apply force to the object, we will change the shape of the object. Okay, so it will cause deform. So today, before we learn about this stress and strain, what is this? We have to learn some force, okay? Tensile and compressive force. So what is tensile? Tensile at here, actually when two force stretch, you stretch. So the diagram here showing you, stretch it. Okay, when you stretch it, this force is called tensile. So when tensile, the force we apply, we stretch the object, okay, the length will increase. Okay, the length will increase. The force we call it as tensile force. Okay, then when we compress, another force called compressive force. Okay, when you compress, so this force called compressive. So we compress it, compress it. When we compress it, actually, we are decreasing the length. Okay, decrease the length. So tensile is increase the length. Okay, so we need to understand about these two terms. Direction of the force that we apply will determine whether the object will extend, will get longer. If longer, that one is tensile force. Okay, get shorter, that one is compressive force. Okay, so this is just like introduction. So we go to your page number 2. Okay, the tensile force and compression force actually can be applied on the spring, okay? In our form 5 or our year 10, we learn about the spring, we hang the things, right? Okay, so at here, a lot is attached to the end of the spring, okay? So we have a load at here. So here, if you getting a load at here, actually, they will pull down, okay? They will pull down or extend. Not only like this, our spring can also put on the ground, something like this. Okay, then we put the object on it, so it will cause a compression. Okay, this one is X. So this one, it will extend X. Okay, so it will cause extend or compress. When we apply a load, actually we give the weight pulling down or pressing down. Okay, the spring that increase in length, so this one we call it as extension. Okay, how much the length increase, extension. Okay, the length decrease, this one is called compression. In IG, we touching with this. We didn't touch it with this compression. Okay, but actually it's applied for extension and compression. Form 5, no problem. You know about this. Okay, so we're having a look. Tensile force. Tensile force is making the length become longer. So how we apply this tensile force on the spring? So we're having a look. Can you see that this part? Increase the length. So this force called tensile force. Then the length that increase we call as extension. Okay? When a spring demonstrates elastic behavior, Elasticity. Elasticity meaning that the properties for the material, they will return back to their original shape and size when the force that we apply, we remove it. So the material can go back. For example, the rubber band, we pull the rubber band. So after that, we release, the rubber band will go back. Okay, that is because the rubber band actually demonstrate elastic behavior. Okay, if they demonstrate elastic behavior, the load applied will create an extension that can be removed so that the spring return to its original length. Okay, the load create extension, but at the end when the load is removed, the spring go back. So we say that, hey, it's display elastic behavior. Okay, but is it forever? My answer is no. Okay, it will until a certain point. The point we call as limit of proportionality. Okay, in IG year 10 we call as limit of proportionality, but from 5 you never touch with this word. It's okay, you touch with the elastic limit. Later on we will mentioning what is the difference between limit of proportionality and elastic limit. It's different thing. Okay, year 10 learn about limit of proportionality. From 5 students, they are learning about elastic limit. It's different thing. Okay, so at here they will be able to go back, okay, original shape and size. Okay, when the spring exceeds the limit of proportionality, the relationship, what happened? If greater, okay, the point exceed to this point, what's going on? The force and extension is no longer proportional. Okay, Hooke's law that we know, F equals to Kx. What is the relationship between your force and your extension? Can you see that F equals to Kx? This is spring constant. It's a constant value. Okay, it's a constant. That means that this value won't be changed. It depends on your spring, stiffness of your spring. So at here, when your force increase, your X extension will increase. Of course, no F, then no X, no extension. So at here, we understand that force and X, okay, if we plot the graph, this one is force, this one is X, we will get a directly proportional graph. Okay, we will get a directly proportional graph. So they say that when the spring exit the point, let's say this is the limit of proportionality. This is the limit of proportionality. Okay, the force and extension no longer proportional. So it might be like curve like this, go up, curving up, curving towards to your X. So in front from here to here until the point, Hooke's law is applied. This one next page I got right. Okay, Hooke's law is applied. Before the point, before we exceed the limit of proportionality, the part, let's say here is O lah. Okay, I put O, here is P. Okay, so for the O to P, before we touch or exceed the limit of proportionality, this region OP actually obey Hooke's law. Okay, obey Hooke's law. But after P, we cannot say that they obey Hooke's law because they start to curve. Where they curve to, they curve towards to your extension. Because now the spring, small force, we already can make it extend a lot. So we need to draw like slightly curve towards to your X, okay, extension axis. Okay, so this one basically also introduction, and some more actually we know already about Hooke's law. So we turn to your page number 3. Okay, what I draw right now, actually at here, page number 3, I go draw again. Okay, so look at here, Hooke's law. What is Hooke's law that we learn? Okay, Hooke's law at here, we say that extension is directly proportional to your force. So your graph should be like this. Okay, provided this sentence apply for Hooke's law, provided the limit of proportionality is not exist. We didn't greater than the limit. Okay, so we say that before that actually is Hooke's law. We obey Hooke's law. Okay, so at here you have to be careful with the axis. The axis can be y-axis is extension, x-axis is the force, or you can be like this. Okay, you can be like this. Force is here, X is here. But before the limit of proportionality, actually, they are the same. Looks like no different. But once we greater than the point limit of proportionality, okay, now the spring no longer obey Hooke's law, no longer directly proportional. It no longer directly proportional. Directly proportional, what is the features? Okay, one, straight line. It must be a straight line. Second, it must be passed through origin. Then we only can say it's directly proportional. Okay, that means that if exceed the limit of proportionality point, okay, so the line will not be continuous straight, it will curve. How it curve, as I mentioned just now, it will slightly curve towards to the x, slightly curve towards to the x. That's why on my diagram here, can you see that it's curved towards to your extension, curve towards to your extension. On my diagram at here, the graph at here, can you show that at O to A is the limit of proportionality. Okay, for this region, O to A, this region is Hooke's law because it is a straight line passing through origin. But if you greater than this point, it will curve. A very small force, but it extend a lot. A small force is needed, but we make it extend a lot, okay? So in our year 10, we learn about limit of proportionality. But in SPM, we talk about elastic limit. In A level, actually, these two things is different thing, okay? So we will learn in more detail. They are different thing, okay? So at here, we're having a look from O to A. Extension X is proportional to F, okay? Proportional meaning that directly proportional lah, okay? So it's a straight line passing through origin. With larger force from A to B, okay, here, when we apply larger force, the spring extend more easily and extension is no longer proportional because now it's curved. It's curved, we cannot say that they are proportional, okay? When the force is reduced, with the spring having being stretched beyond point B, it will no longer go back to original length. Okay, if goes to here, we release. Okay, we remove it. It already achieved the elastic limit. We remove the loop. What's going on with the spring? It will go back a bit, but not all. Basically, your spring is already deformed. Okay, already spoiled a bit up. Okay, it cannot go back to original shape and size. Okay, so at here we're having a look. What is the limit of proportionality and what is the elastic limit? Okay, limit of proportionality actually is the point. If we beyond this point, your extension is no longer proportional to your force. Okay, beyond this point, Hooke's law doesn't apply. Okay, elastic limit is value of stress. We will learn about how to calculate the stress. Okay, we will learn about this, but right now we're having a look first. Stress is actually force divided by area. It seems like we calculating the pressure and force divided by area. So the stress unit actually also Pascal. Okay, the value of stress beyond, okay, which an object will not return to original dimension. It won't go back to original dimension. The length is permanently spoiled. Okay, so in our year 10, we already learned what is Hooke's law? F equals to kx. K is a spring constant. Okay, K is a spring constant that we use to measure stiffness of the spring. Okay, stiffness, that means hardness to extend. Okay, so if your spring constant is K, this K value is big or high, that means that this spring actually is stiffer spring. It's hard to extend or compress. Okay, so at here, how we do calculation for this spring constant from the graph? Okay, so just now the graph at here like this, like this. Okay, if let's say this is F, this is X. Okay, the gradient like this. Because now we're talking about Hooke's law. So I just draw the straight line. I don't draw other thing. Okay, Hooke's law. Now we're applying Hooke's law. So what is the K? You can calculate the gradient of Fx graph. So the gradient is y divided by x. Okay, y2 minus y1 divided by x2 minus x1. So it should be f divided by x. So if I rearrange from this formula, k is f over x. So we can using gradient of the graph to find out what is your spring constant. Okay, then just now I got told you we got two ways to plot the graph. Okay, not necessarily must be force on y-axis or must be on the x-axis. So if let's say now the graph is like this, here is force, here is x. Okay, we're talking about Hooke's law, so I didn't draw the curve part. Okay, here I cannot say that gradient of fx graph is my spring constant. I cannot say so. Right now, I cannot say so. Why? Because if based on this graph, xf graph, f over f, x over f, this is not a spring constant. So for this graph, your spring constant k actually is 1 over the gradient. Okay, that means that you have to upside down the gradient. Okay, you have to upside down 1 over the gradient. Okay, so this one, when you do the partial question, okay, please have a look what is the axis. Okay, so boys and girls, until right now we are going to try our partial question. Okay, turn to your page number 4. This is 2024 last year partial question. Okay, boys and girls, a force extension graph is produced for a metal wire. Okay, so they plot a force extension graph. What must describe the limit of proportionality of the wire? What is the limit of proportionality? Okay, like boys and girls, tell me your answer. This one easy. Is just make sure, correct, Wesley? Vashini, correct. Farwell, correct. Farwell, very fast. Okay, like dear. Answer is B. Is the point. If exit this point, Hooke's law will not be obeyed. Okay, Hooke's law will not be obeyed. A Prasan is here. Okay, like dear. Number 2. Okay, when a force applied on the spring, the length of the spring is 90 mm. When another force 1.3 applied to the same spring, its length is 115 meter. The spring obey Hooke's law, so F equals to Kx. What is your spring constant? Like boys and girls, can you try? Can you try? You're right, correct. Farwell, no, try again. Vashini, correct. Vashini, tell me how you solve it. How about others? How about others? Like boys and girls, try. Fatima, correct. Any others? They obey Hooke's law. That means that the spring does not spoil. The K here is the same. Okay? Same spring. Okay, like dear, same spring, so they were having same K. Every single spring have their own spring constant. Okay? Wire cannot Jorea, wire cannot return to original length that is related with the elastic limit. After we goes to this point, it will not be go back. It will goes to this area. So they will have a certain increase in length at the end. It won't go back to original length. Okay, for the C. Like dear, let me have a look. Okay, correct, Washini. Same as me. Okay, F equals to Kx, dear. F equals to Kx. So from these two, actually, just now I apply 0.8. Now I apply 1.3. What is my extra force applying on this same spring? Okay, so I can using 1.3 minus 0.8. K is a spring constant. The X extension. How much I extra extend due to this extra force. Okay, I apply extra force. So how much I extend? Okay, extend. So at here, this one is, you see here, dear. Okay, don't forget about this one, Newton per meter. So we have to convert mm to meter. Okay, so at here, this one should be 0.115 minus 0.09. So your answer for this question should be 20 Newton per meter. So answer should be donkey. Okay, I can using this is because they still obey Hooke's law. So I can using F equals to Kx, and then the K actually is the same K because they apply on the same spring. So I can just using this, we trying to find 1.3 to 0.8, how much extra force they apply. Then how much extension they extra, we get extra due to this force. So answer should be donkey. Okay, number 3, right dear, number 3. Based on this graph, do you able to identify which spring, identify their spring constants, and then you arrange show decreasing. That means that the first one should be the highest spring constant. Okay, so you try. Just now I already teach you how to find the spring constant. So you try. Fatima, correct. Fawal, correct. Fawal, just now the question 2. Do you able to get the idea? Okay, good job. Okay, Vashini, correct. How about others? You're correct. Good job. Okay, dear. Just now I got told you this spring constant is K. K is force divided by X. From this graph, actually is calculating the gradient. Okay, for this graph, it's straightforward. We calculate the gradient. Wesley, correct. Hai Chen, correct. Good job. So at the end, you compare 10 divided by 5. So it's 2. So this one 20, 5. Then this 100, 0.1. This is 1000, is it? My mathematical problem or not? 10 divided by 0.5. Ooh, 10 divided by 0.5. 20? 20. 100 divided by 0.01. 100 divided by 0.1. 1000. So, okay, our answer will be B, boy. Okay, so this one is the highest, followed by this, followed by this, and last one is this. So no problems, right? They just testing on you. Do you know how to get the spring constant? Okay, Manjo, correct. Right there, we goes to your page number 5. We goes to page number 5. Okay, for this question, they are quite straightforward. They might be exchange their axis. So if they exchange their axis, you still calculation gradient, but your spring constant should be 1 over the gradient. Okay? So for this one, be careful. Do not just look at the graph, then straightly calculate the gradient. No. Okay, like deal. Comes to page number 5. Question number 4. Okay, you try first and at the same time I take attendance. Jahan. Jahan is here or not, Jahan? Boyang is here, right? Boyang, I think you absent for a few weeks, eh? I thought you are not here anymore. Boyang, the previous lesson, if you already missed, you contact me. I share you the Zoom video you study. Okay, dear Kai Chen, correct. Wesley, no. Try. Wesley, no. Vashini, correct. Fatima, correct. Prasan, correct. Vito, correct. Okay, dear, here. Spring constant, cannot directly get gradient because now they exchange the acids, see? Okay, the exchange. So what should we do? The K actually is 1 over gradient. Okay, the gradient that you get actually is X over F. Okay, so we need to 1 over it so that we can get the F over K lah, to get your spring constant. Farwell, correct. Okay, like dear. So at here, 1 over your gradient is, okay, 15 cm. But here, can you see that? cm. So here is meter. So we have to convert times 10 power of negative 2. C represent times 10 power of negative 2 divided by the force 6 Newton. So at here, my answer is 0.025. String constant is 1 over 0.025. So your answer should be 40 Newton per meter. Answer should be donkey. So in A level, actually, they trick you in prefix also. So we have to be careful. Always observe the prefix, okay, the unit. Okay. Oh, unit, yes, Manjo, unit. Okay, like dear, we goes to the next question. Be careful with unit. Okay, like dear, next. A metal wire P obey Hooke's law is stretched within its limit of proportionality. Okay, obey Hooke's law. So on figure 4.1, sketch the variations of tensile force in the wire with its extension. The force that we apply called tensile force. Okay, so since obey Hooke's law, so at here obey Hooke's law, it must be force directly proportional to your extension. Directly proportional means that, okay, like this. Okay, so obey Hooke's law must be force directly proportional to x. Directly proportional got two features. One is straight line. Second one, start from origin. Okay, so you think without the force, of course, no extension. What? Without force, no extension. So it must be start from 0. Okay. Can you state the name of the quantity, physical quantity here meaning quantity is talking about physical quantity, represent by the gradient. So gradient can represent what physical quantity? First lesson we talk about physical quantity is the quantity that can be measured. It will give you value and unit. That is called physical quantity. Okay, like boys and girls, tell me. When you calculate the gradient, actually is represent what physical quantity? Yes, correct. Thank you, Prasan. Yes, correct, Vashini. Wesley, yes, correct, Wesley. So at here, what they represent? They represent spring constant. Okay, for example, at here, let's say this one spring constant 40 Newton per meter. This is called magnitude. This is called unit. So spring constant actually is a physical quantity, because it consists of magnitude and unit. It can be measured. Spring constant can be measured. So at here, they're asking you, when you calculate the gradient, what are you actually represent the quantity? Actually, is spring constant. Okay, spring constant. Last time we learned about inertia, right? We said that inertia is object at rest. It will keep on at rest. Object moving, it will keep on moving. Is there any formula for us to do calculation and get the value for inertia? For Newton's first law? My answer is no. We only know that the mass increase, then inertia effect will increase. That's all. So at here, can I say that inertia is a physical quantity? My answer is no. Inertia not a physical quantity. So I emphasize physical quantity must be a quantity that can be measured. Since you can measure, of course, it will give you magnitude and unit. Thank you, Farwell. Yes, the answer is no. Inertia is not a physical quantity. Okay, like boys and girls, goes to next question. Okay. So a spring is suspended from a fixed point at one end. Okay. So at here, spring suspended. The spring is extended by a vertical force. Okay. So at here, extend by a vertical force. Okay. For example, something like this. To the other end, the variation of force and the length is shown. Okay. Teacher, you told me it must be straight line passing through origin, but this graph is not from the origin. It's okay. You learn in year 10 and form 5. So please later on answer by yourself. State the name of the law that give relationship between force and extension. In this graph, here is force. But this one, they say L, length. They're not calling this as extension. Okay? If this part is extension, it must be a straight line passing through origin. But this is length. Okay? So what is the name of the law that give a relationship between force and extension? Thank you, Farwell. Yes. Hooke's law. Hooke's law say F is directly proportional to X, provided not exceed limit of proportionality. Okay, boys and girls, can you help me to calculate the spring constant for this diagram? Now how to calculate the spring constant? Now, boys and girls, count for me. Yes, Manjo, what is the unit? Vashini, correct. Fatima, what is the unit you use? You look at the box, no, the answer here. They're giving you Newton per meter, dear. So, Fatima, you try. No, your answer is not in Newton per meter, Fatima. Fawal, no, you must be, yes, correct, Fawal, right now, correct. Right. Manjo, correct. Wesley, no, Wesley, I think your unit conversion is something wrong. Prasan, correct. Kai Qian, no, I think the reading that you take slightly wrong. Okay, you check again the reading. Jore, correct. Jore is correct. Fatima, correct right now. Okay, dear. We understand that spring constant force equals to Kx. I want to find this spring constant. Okay, so I can rearrange F over X. Okay, the force that we apply from 0 to 12. So I can put at here 12 Newton. Okay, actually, because this question, they already want this in Newton per meter. If they didn't mention about this, actually you want to using mm also no problem. You can using Newton per mm, no problem. But the problem is here, they want Newton per meter. So we have to convert to meter. Okay, X is extension. How much is extend? Like boys and girls, teacher, why you are not starting from 0? It's because this is length. When without any load, we already have the length. This is your length. What is my length? My length is, this is original length. Okay, my length is xcm. Okay, then after I apply 12 Newton, I found that my total length is 24. So at here to here, I found that my new length is equals to 24 cm. How much I extend? So from here to here, okay, is my extension X. So my extension should be using 24 minus 8. Okay, 24 minus 8. So you have to convert the 24 cm to m. So you will get 0.24 minus 0.08. Okay, this one is 0.24 m. This is 0.08 m. So make sure you do conversion correctly. Okay, so at here, this is in meter. Your answer should be 75 Newton per meter. 75. If they didn't mention at here, you want to using mm, no problem. Write your answer in Newton per mm, no problem. But the problem is right now they want Newton per meter. Okay? So boys and girls, any question? No question, we go to the next page. Give me some response. There's a button there. You can give me response. Then I know that you understand. Then we can proceed. Thank you, dear. Okay, we go to next page. State the Hooke's law. What Hooke's law say? Like boys and girls, I give you 1 minute to complete it. Hooke's law actually is extension directly proportional to the force, provided you does not exceed the limit of proportionality. Okay, 1 minute for you to complete this. That means that this one is 2024, also last year. Okay, that means that they will asking about Hooke's law, so you have to know about Hooke's law, saying extension proportional to force, provided the limit of proportionality is not exceed. Once you exceed the point, Hooke's law does not apply anymore. It won't be continue give you a straight line. It gives you a curved line, and this curved line will curve towards to your extension part. Done? Writing down your definition for Hooke's law. If done, give me response, then we proceed to the B, 7B. Okay, thank you, Wesley. How about others? Yes, Fatima. Okay, good job. Like dear, here. Before I guide you, can you try first? Okay, the variations of the applied force with the extension, force against extension. The sample behave elastically up to an extension of 80 mm, and it will break at point X. The question wants you to draw a cross to show the limit of proportionality. At what point is your limit of proportionality? Can you find out the point and then label with the letter P? Then you type in the chat box, tell me that roughly is what, not roughly, it is at what position, coordinate. Found out it have a very clear coordinate. Your coordinate is not the correct coordinate. At what point? It have a exact point. Like how about others? How about others? Fatima also no. Like, let me check. Wesley, the first coordinate is correct. Fawal, still no? Try again. Oh, okay, okay. But the point that you give is correct. Yes, Vashini, yes, correct. Wesley, correct. That is the point. You label it. Okay, label the point. Label P. How about others? Let me have a look. Manjo. Yes, Manjo, correct. Okay, dear, I teach you guys how to do for this. Vitor, let me have a look. Vitor, no. Vitor, y-axis correct leh. But your x-axis is wrong. That means that you get the correct point, but you take the reading on the scales is wrong. Vowel. Vowel correct. Yes, vowel correct. Okay, dear. I teach you how to do. Actually, it's easy. You put your ruler. Okay, turn, 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 turn. Okay, turn, 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 turn. Let me have a look. Turn, 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 turn. Okay, boys and girls, at here. Where is the point? It will be at the point before it become curve. Okay, it's the maximum point. So at here, the coordinate should be at 60, then 5.4. So at here, 5.4. Here, half of it. 1, 2, 3, 4, 5. 5.4. So this is the point. Oh, you very hard. Hey, this is the point. I think this is the point. Wait. Okay, here. Point what? Point P. Oh my God. This is the point P. Okay, at the coordinate 60, 5.4. So you have to read lah. 60. 60 is the half of it. Here going down. Yeah, here is half of 40 and 80. So this is 60. Okay, when goes here, actually this part is too hard for me to draw. So basically it's 5.4 at here. 5.4. Okay, boys and girls, so I repeat how we find this point. Because we understand that it will be a straight line, okay, before it become a curve. So we can put our ruler like this. Put your ruler. The point that is still follow the straight line before it become curve. So at here, actually here the answer actually is 60, then 5.4. Okay, this is the point P. Okay, next. Okay, next. Wait, let me have a look. Okay, on the line in figure 3.1, can you draw a cross to show? Oh, draw a cross. I didn't read. Cross. So please draw a cross. Follow it. If you didn't follow, then no marks. On the line, draw a cross to show elastic limit. Teacher, how I know? Elastically up to extension 80 mm. That means what? Elastic limit at 80 mm. Okay, so this is the point. So at here, we have to label at here, somewhere here. This is your elastic. Okay, so this point is at 85.9. How I know where is the elastic limit? They told you elastically up to this extension 80 mm. Okay, so any question for the Hooke's law, finding the spring constant? No way is your limit of proportionality. No way is your elastic limit. Is it okay? Okay, thank you. Then we go to next part. Okay, combination of the spring. Okay, this is a new thing. We learn how to calculate the spring constant, okay, in the combination of spring. In series, before that we recall a bit, okay. In series, if we apply a force, actually the spring in series, both of them will experience both force, okay. Both of the spring will experience the force. Okay, not only on one spring, is both of them will experience same force, the F, okay? So extension, it will extend X. It will extend because we're pulling down, so it will extend. So in this system, X plus X in total, we will extend 2X. Okay? If you got N spring, same number of spring, the total extension should be NX. Okay, how we calculate overall? If I want to assume this is a one single system, okay, spring system. So how can I do some calculation to find out the spring constant? So spring constant is 1 over total K equals to 1 over K1 plus 1 over K2. This is how we find the overall spring constant, okay? For the parallel, Parallel at here, when we apply the force, the spring doesn't experience force it doesn't experience the full force, because when they connected in parallel way, they are sharing out, they share out the force. Okay, you can imagine you standing at here, your friend standing at here, you both of you carry a things. If you carry a things together, so it's not that heavy one. Okay, because it will be shared out, the weight, it will be shared out. So at here, the tension at here is force divided by 2. So force divided by 2. Extend, of course, your force become half of it. You won't be extend fully extend. You will extend x over 2. X over 2. Overally, you extend x over 2. I extend x over 2. In overally my system, I only extend x over 2. I don't need to add it up. Okay? So this one x over 2. If there is end spring at here, the extension can be shared out by the spring. So the total extension actually can be reduced. So in order to find out what is the total spring constant, you add it up, the spring constant for each spring. Yeah, Wesley said it's like opposite to how you find resistance. Yes, in series for resistance we add it up. In parallel of resistance we have to 1 over plus 1 over, then inverse it. Now this one is similar but it's opposite way. Yes, correct, Wesley. Okay, dear, here K is the overall spring constant equivalence, spring constant, then spring constant 1, spring constant 2. Okay, like boys and girls, we try and see what kind of past year question they will ask. Okay, next question. This is 2024, last year. A spring have a spring constant 6 Newton per cm. It is joined to another spring which is 4 Newton per cm. A load of 80 Newton applied. So they actually got two ways to solve. Dear, actually got two ways to solve. You can using your Form 5 method, okay, to count each of them how much extension you get. This is one of the method. Or today we're using the method that we learn right now. We make calculate what is your total spring constant. Then F equals to Kx, total force, total spring constant. The force is here, F. This F acting on a single spring. So at here, what is your extension? Okay, like boys and girls, you try. Two method can find. Both method will give you the same answer. One of the method is the last times from 5, we learn count for each of them, the extension for each of them, then we add it up together. Wesley, not this answer. Try. Fawal, not this answer. Hey, two of you get the same answer. How come? Washini, correct. Later on, Wesley and Fawal tell me why is your answer, your idea is wrong. We have to find out why it's wrong. Then I will know that how the students thinking about that. Manjo, correct. Did you calculate? No, Wesley. The 6 Newton per cm is not extension. It's not extension. So you cannot really add it up. No. Then you add it up is 10 then. Wait. Oh wait, what Wesley add both. Wesley, this one how you find the, yeah, cannot. Kai Chen, no? Kai Chen same idea with the Fawal and who? Wesley. So must be you guys must be got something idea together, but the idea is wrong. I want to know what is the idea. Fawal correct. Fawal, can you tell me why just now you give the answer of that A? Okay, now I show you, dear. We using method 2. Method 1 today. What is the method that we learn? 1 over k total over 1 over 6 plus 1 over 4. So at here, when you do calculation, k total, I assume this is a single one. It will be 2.4 Newton per cm. So if I redraw, I can assume this is a single big spring. Okay, so this is the force 80 Newton. So my K actually is 2.4 Newton per cm. So F equals to Kx. My force is 80. My K, I don't know. I know the K. K is already calculated 2.4. My X, I don't know. So my extension is 33 cm. My answer should be donkey. Did the same method, yes, until I realized it is spring constant. Ah, yeah, okay, I get it. So Wesley, the 6 and 4 is not extension, it's spring constant. Okay. So there is many ways to solve, many way to solve. You can using F equals to Kx to find the extension for this, then you add it up together. This is last time what we learned. But today we learn we can calculate overall spring constant. Okay, right dear. If no question, we goes to the question number 2. Is it okay? Okay, good job. Right dear, can you try question number 2? You try, then at the same time, at here I do the method, another method to show you. Okay, you continue with question number 2, Okay. Here. Okay, boys and girls, I complete the question 1 with using another way to solve it. Okay, found out question 2 wrong. Okay, so you can have a look. I split out because 80 Newton will be experienced by each of them. So each of them will get 80 Newton, 80 Newton acting on it. So I calculate if only this 6 Newton per cm, how much extension it get. If only for all 4, how much extension it will get. So I add it up together, I will still getting 33. Eh, why? I think Fawal and Wesley can be best friend. Two of you getting the same answer, but both of you the answer is wrong. You're correct. I think Wesley and Fawal idea is quite close. Your idea, your frequency. Okay, Vashini correct. Kai Qian no, Kai Qian is same group as Fawal them. Okay, so if you get B, it's wrong. Answer for this question is C. Okay, answer for this question is C. Okay, how we get C, dear? F equals to Kx. So this is 1.6. They're asking you overall spring constant. So we want K total. Okay, so total force is 1.6. Total spring constant, we don't know. This is what we are going to calculate. Total extension, 0.4. So K is 4 Newton per meter. Okay, this one, total force is 1.2. Total K for overall, I don't know. Okay, we are going to calculate about this. Total extension, how much is extend? As I told you, we are parallelly extend. So in overall system, we only extend 0.075. Follow this. Okay, K will equals to 16 Newton per meter. I think maybe you wait, have a look. Overall has an overall. Yeah, I think it's because you are not using this. Extension is 0.075, is it? Okay, here. Next, this one, if you do it properly, okay, here F equals to Kx. Overall force is 1.8. K overall, we don't know. Total extension. This one is extend here and extend here. So 0.075 plus 0.15. My answer for this is 8 Newton per meter. Okay, for this, we can separate in this way to have a look. Okay, separate it in these two way. So F equals to Kx. Overall force is 2.4. Overall K, we don't know. Overall extension here and here. So it's 0.15. So K is 16 Newton per meter. Okay, is that clear for this part? Okay, Wesley, you thought you have to add it up when they are in parallel? Oh, no, dear. You miss extension, right, Wesley? Okay, you see, initially, okay, maybe it's like this. How should I draw? Okay, like this. Initially, like this. Then after that, I extend a bit like this. Okay, my friends parallel with me also extend like this. So basically, two of us in the overall system, we only extend 0.075 meter. I think you confused with spring constant K. This is extension. Their extension will be the same. Let me go back. Obviously, this part. Can you see that this part? It extend x over 2, x over 2. But overallly, the system is extend x over 2. You don't add it up because you are parallelly increases. You don't overallly adding the extension. Okay, here, next year. Like boys and girls, can you go to the question number 3? Yeah, you try first. In parallel, Wesley, if parallel, the add it up actually is the spring constant to add it up. Extension, we don't add it up. Can you go to the notes? Where is the notes there? Is it this? Prasan, is it this? Okay. Three springs are arranged. No, is which one? This one? Combination. Is it this? Find the upper K, find the bottom K, find the overall K. Okay, boys and girls, question number 3. In this system, can you find out the total K? Then after that, using F equals to Kx. What is your overall force? What is your overall spring constant? And then rearrange, find out the extension. Prasan is done, let me know. Then I will go back to page number 10. Okay, Dana. No idea? They want to know increase in the overall length of the arrangement. Okay, when the force is W. So this one overall total extension, total force. So you have to know what is total spring constant. You can think like resistance. Yes, just now Wesley mentioning about similar to resistance, how we calculate the total resistance, but in opposite way lah. In resistance series, we add it up. Parallel, we 1 over, okay? Now, we opposite way. Parallel, we add it up. Then in series, we 1 over. Any of you? PQ has spring constant K. Here is also K. So R is 3K. Kai Chen can try one more time. Washini correct. Jore correct. Prasan correct. Fawang no. Can try one more time. Wesley correct. Manju correct. Kai Chen can try. Can try one more time. What is the total spring constant? Okay, dear, we can share what I want to say. Okay, you can solve this first. Okay, solve this part first. Since it's in parallel, so it's in parallel, so we need to add it up together. So for the upper part, the spring that I combine, let's say I already combined, then after that, this is the bottom part. Okay, so this is 3K remain. So the upper part here actually is in parallel. Parallel, what should I do for the spring constant? Add it up together. So it should have 2K, right? So from here, I can simplify to become this, okay, 2K. So from here, how can I go to the single spring? So I should put in series, I should 1 over K total equals to 1 over 2K plus 1 over 3K. Okay, so what is your K total? Use your mathematic move here, there. That is not under my topic. It's your topic. Okay, mathematic move. Pa. Okay, then you will get 6K over 5. Okay, 6K over 5. So I put in here 6K over 5. What is your extension? Total extension. Total extension. Okay, I move 6K over 5 to another side. So it will become 5W over 6K. Answer will be A. Is that clear, dear? Is that clear? No response? Thank you, Wesley. How about others? Kai Chen, okay, Kai Chen. Okay, Kai Chen, is it you do this part is something wrong here? I think it's this part. Maybe you're not familiar with the formula yet. Is it spring constant? Total spring constant? Why use 1 over K? Okay, why use 1 over K? This one. It's because from here, I simplify to become a single spring. Okay, Fawa, I become a single spring. How can I become a single spring? Come back to here. If in parallel, our K is added up together. Okay, in parallel, our K1, K2, we just add it up together. So we come back to this question. K in parallel, I just add it up, so I get 2K. After I get 2K, this is a single spring. It will form another series with another spring. If in series, 2 spring in series, we come back to here. 2 spring in series, this one. 2 spring in series, we have to using this formula 1 over K equals to 1 over K1 plus 1 over K2. So far well? Okay. Okay, Kai Chen. No, I use K only. Okay. But now, Kai Chen, is it okay? Oh, here. Like boys and girls. Okay, the last question for this lesson, for this worksheet. Okay, the lamp is suspended in equilibrium. So here. Okay, equilibrium from a fixed support by the tree. So initially we got 3 wire. We got 3 wire to support it. Okay, the weight of the lamp cause each wire to have extensions 0.4. So the weight cause each of them having 0.4. So in overall it's still 0.4. Okay? Parallel, the extension in overall is still 0.4 because parallelly increase, so overallly your system is increased 0.4 only. The height hedge above the flow, okay, of the lamp above the flow. Okay, that means that, for example, here, this is my flow. This is my flow. So this one, the hedge, I measure hedge. Okay. Overallly, this tree increases extension 0.4 cm. Okay, there is a weight here acting downward. Okay, the middle wire suddenly break. Okay, if they break, they only left 2. Okay, if black is only left 2. So at here, this is my weight. Okay. Then a small distance as the extensions of the remaining 2 wire increase. Okay, dear, can you see that when I slightly draw a little bit lower? It's because when you only got two wires to support, of course, it will extend more. That's why when I draw only two wires, I draw slightly lower a bit. Okay, not only two spring to support it, so it will extend more. Okay, then the wire still obey Hooke's law, so we still can using the formula F equals to Kx. When the length is in equilibrium, that means that they didn't break, they still support. The H is measured again. Okay, this is the H. So just now the H. So now this is the new H. H2. Okay, just now the one I label H1. They asking you what is the difference between these two H. H1 and H2, what is the difference? So boys and girls, you have to find out, okay, what is the extensions? Let me have a look. Or let you think first, okay, how you find out H1 and H2. Actually, you count and then you find. Let me have a look. Wesley, let me have a look. Where total? Can you go back to egg for 5 seconds? Egg, patch egg or what? Like Wesley, patch egg or what? Is it this? Patch egg, yes. Like Wesley. Okay, initially it's 3 spring. So what is their spring constant? What is their extension? So that one you get the force. Okay, that one you get the force. Then after that, Prasan. Oh, Prasan so fast. Yes, Prasan. Prasan, your idea is so good. Okay, so this one also experience a weight. F equals to Kx. They were having same weight. W. Or I put F, okay? They're having the same F. Then when three wire in parallel, what is the spring constant? And how much it extend in your overall system? Then when only two wire, what is your extension? Well, no. No, you try. Jore correct. Washini correct. So F equals to, initially this one overall, K overall is 3K. 3K, add it up together, 3K. So this is 3K. How much is extend? 0.4. Okay. Then, when only two string, so F is still F because the weight still the same. The length still having the same weight. So F is still the same. But the K at here right now only 2K because only two springs to support 2K. How much is extend? I label X2. Okay, X2 here. So your extension 2 is equal to F over 2K. Your F actually is 3K times 0.4 divided by 2K. Am I right? So you will be able to calculate how much is extend in your X2. Okay, the difference between H1 and H2 actually is different between this. So next, Fawal correct. You already get the idea, right? Okay. So boys and girls, here the main things that you have to know is the force for both cases are the same. These force are the same. Because from starting to ending, we're still using the same length. But just three wire and two wire different, their spring constant will be changed. Okay. So at here, I understand that my force is 3K times 0.4. So same force apply to new case. Okay, 2K because two wire. Extension is 3K times 0.4 divided by 2K. It's just formula. So at the end at here, I will get 0.6 cm. So actually in overally, I will extend 0.6 cm overally. But now the question asking you what is the difference between two hash. These two hash actually is same as here we finding the difference between hash x2 and x1. Your x1, x2 is extend 0.6, x1 is 0.4. So your answer is 0.2 cm. You see, if I write 0.2, I cannot score the mark. 0.20, two significant figure. Okay, this question a bit tricky. It needs you to think. Okay, what is the same constant value? Okay, then you have to using your mathematics. That's why when we learn physics, actually our mathematics must be good enough. Okay, because we involve like simultaneous equation, cosine, sine, tangent, and so on. Okay, that assume you're already very good in mathematics. So you do substitution in. At the end, you get what? You get the extension for 2. Extension for 2. Okay, extension 0.6. So how much we increase? We lower down. We lower down extra 0.2 cm. Okay. So your H1 and H2 also different 0.2 cm. Okay, is that clear for this question, dear? Okay, thank you, Farah. Thank you, Wesley, Vashini, Kaichen. Okay, so we can go to lesson number 24. Okay, so just now we got mentioned elastic limit is talking about the stress run, right? Okay, we go to your lesson 24. Okay, behind the exercise, all the answer I provided at the bottom part, you try by yourself. If you really need some working state and you cannot solve it, then you find me. Okay, answer is here. Like boys and girls goes to lesson 24. Okay. Are you ready, dear? Yes or no? Are you ready to learn? Okay, thank you. Like dear. Okay, stress and strength is the main thing that we want to learn in this chapter 6.1. Okay, so what is stress? What is strain? Okay, when stretching different materials such as metal wire, the stress and strain will be more useful to represent it, or not only force and extension. Okay, in O level, in SPM, we learn about force and extension only. But is there any more useful information to talk about the material? My answer is yes. That's why we learn about the stress and strain. It's more useful. Okay, so stress symbol is like this. Okay, like this symbol. This is the symbol. Stress. Stress actually is normal force per unit cross-sectional area. So force divided by area. So it's same like we calculating pressure, force divided by area. That's why the unit are the same in Pascal. You want to be in Newton per meter square, also no problem. Newton per meter square, yes. Okay, here I want to emphasize when we want to calculate the stress. Here this area, you have to know how to do calculation by calculating this area. This area must be pi d square over 4. Why is this? Because pi r square. Most of the time, they don't want to give you r directly, they give you d. So if you give d is pi d over 2 square. So at the end, we get this. You have to know how to calculate the area by using pi d square over 4. Okay? So, Wesley, you get it? For this one, pi r square. But most of the time in our A level, they don't give you the r directly. They want to give you d. So when we do substitution for the d into the formula, it should be d over 2. So d square, 2 square, it becomes 4. That's why I want to emphasize this, okay? Because most of the question will be trick you in this way. Okay, here another things that I want to emphasize is they like to asking you how you measure the area. What instrument you use. Okay, area we can using micrometer screw gauge. Okay, So this one is another vernier scale, also can. Okay, they would like to ask you how you calculate the stress. Okay, by what using what instrument. So this is the answer. Huh? Okay, tensile force stress is the maximum force that we can apply until what until okay per original cross sectional area a wire is able to support. Okay, so this is stress. Strain is extension per unit unstretched length. This is that means that original length lah. Original length. Okay, the formula for this will be like this. The strain will be like this. Symbol strain equals to the extension divided by original length. Okay, write down. Vernier scales I'm not going to teach right now. But if one day we're doing practical, we need to using the vernier scale. But my school, our vernier scale is very convenient. It's digital. Last time in when we study about the SPMs, we're using the vernier, but now the vernier and micrometer school gets already out from your syllabus, no matter you are O level or SPM. It's already take out. So this I know that this instrument is new things for you right now at this moment. Okay, but right now I'm not going to teach you how to read it. It takes times for us to I need worksheet to tell you that how to read it. Okay, so that one is when we doing the practical, I tell you. Okay, during the practical I tell you, but I just let you know that there is something like this. Okay, like dear. Okay, this is extension divided by the length. You see, this is meter divided by meter. So cancel the unit. There is no unit for strength. No unit for strength. Okay, like boys and girls, we go to the next page. Is it okay? Okay, next. Young modulus. Okay, we want to know about Young modulus. It can measuring the stiffness of the material. So previously in O level, we learned about spring constant to measure the stiffness. Actually, in more correct or more useful way, we can using Young modulus. Young modulus actually is the ratio of stress and strain. Okay, so at here, E is equals to the stress. Stress is this symbol divided by the strain is this symbol. Okay, then if I do substitution for this one is F over A. I write it here, F over A. Okay, for the strain, for the stress, divided by the strain. Strain is extension over the length. So if I rearrange, I will get F over A. Then this one L upside down. This one, do you understand how I get it? Okay, I'm using this divided by the strain. Stress divided by the strain. Okay, this formula is very, very important. So using a highlighter, draw it up. Very important. Okay, here. Can you see that this one, F divided by X? F divided by X. Actually, what is this? This is our spring constant. Sometimes in your A level, they won't give you F and X value, but they give you the graph. So we can calculate the gradient to find the spring constant, and then these two value they will give it to you. Okay. So here, next here. Okay, you see, if we want to find the Young modulus, we can plot the graph. Stress divided by strain. Y divided by X, this is gradient. The gradient represent your Young modulus. The gradient represent your Young modulus. Because the gradient actually is y-axis divided by x-axis. In this part, is your stress over your strain. So this is Young modulus E. Okay, dear, we go downstairs here. You have to roughly got idea how you measuring. You do experiment to measuring the Young modulus. Okay, some of the past year they're asking you, they might be give you like 3 to 4 marks. Okay, how you do your experiment and then you find out your Young modulus. Okay, here this is the answer. So here, measure the diameter by using micrometer screw gauge. So you have to mentioning what instrument you use. Okay, what instrument you use. Taiqian, you want me to scroll up for which part? Is it this? Okay, give you 10 seconds. Taiqian, if done, let me know. Okay, done. Okay, like dear. So first you have to mentioning what you measure. You measure the diameter. Diameter is because later on we are going to calculate the area. Okay, area. So we need to calculate the diameter. You're using micrometer screw gauge, okay? The weight, measure the weight. What is your load? Because we need to know the force, okay? So what is the load? Measure the original length. You're using what? Meter rule, okay? Meter rule. So your original length at the end at here, this is the original length. So we have to measure this, okay? I already measure the length, measure the area, measure the load, okay? Then you need to measure the extension. So I need to measure this. So in this formula, you have to think how you get all this F, L, A, X, how you get this. This one you measure using your spring to know the weight or to know the load, okay? The L is original length using ruler. Okay, area using micrometer screw gauge, measuring the diameter. Of course, after you get the diameter, please calculate the area using the formula. X is the extension using original length minus the initial original length new length minus original length. Okay, so at here they might be giving you a graph force against extension. This is what I told you, force against extension. They might be give you the graph. If they give you force against the extension, actually this one is the gradient that you get is already represent F over X. So you just substitute inside here. So this is your gradient. This is your gradient. Okay, this is your gradient from the graph. Of course, you don't want to put the graph, then you can measure every single of them. Okay, so at here, your Young modulus can be used gradient times L times L, times L over A. Okay, this is roughly the way how we find the Young modulus. Is that clear? Is it okay? Any question you want to ask me? Like dear? Okay, Papa, okay. How about others? Okay. Right there, another method you can using pulley system. Okay, another method you can using pulley system. So you attach a thin wire sample with a non-length. Okay, you already know the original length lah. Okay, so actually you have to measure also. Then you also have to measure the area. This method actually is simplified already lah. If more in detail, you have to mention like just now. Okay, measure the diameter using what. Then continue add your load. Okay, measure the extension. Okay, calculate the stress and strain. This one slightly different is they count stress and strain. Just now is they plot the graph for F and X, but both methods are correct. Okay, both method will give us the answer. Okay, so for this one, they plot stress and strain. Stress and strain. Okay, so for this, the gradient actually straightly is Young modulus. Okay, you can using force against the extension, the graph, and then substitute all others information to find E. Or at this method is they trying to calculate the stress and strain, plot the graph, find the gradient. Actually, it's same thing. Okay, so same material will having same Young modulus. It's something like you having the same material for the spring, you having the same spring constant. Am I right? Okay, right dear. We try for the past year question. A steel wire have a length 300 cm. Okay, be careful with unit cm. Here is m. So we have to convert it. Okay, so this one is your original length. Okay, cross-sectional area. This is area, but please remember millimeter square. Convert it into meter square. Young modulus. So this one is in. Okay. One end of the wire is attached to a fixed point, a load. So this is your force F. Okay, the wire obey Hooke's law. So F over K. This one is applied. Okay, can you calculate? E equals to FL over AX. Okay, all the information is already here. What is the extension? Okay, calculate extension for me. But the problem is, please make sure you know how to do conversion. Wasini correct. Rashini, you can try with question number 2. Conversion of unit in AS, they assume actually is basic questions, so you have to know. No, Manjo, you can try again. Maybe some substitution is wrong. How about others? Only 2 of you complete? Hai correct. Jore leh, Jore. Jore no. Manjo no. Is it conversion wrong? Okay. Check which number that you put is different with me. Different as me. Here. This is my answer C. My answer should be C. Conversion for this part and this part. Please make sure it's correct. Manjo, check which part is wrong and identify the mistake. Is it okay for question 1, dear? If okay, then I'm going to question 2. Any of you? Okay, Wesley, okay. How about others? Fatima, okay. Vashini, okay. Manjo, Fawal, okay. Good job. Right, dear. Next. What is the force? Wire have a length, so this one is L, original length. Diameter, they give you D. So you have to calculate area by yourself. Then this one, Young modulus, G. G. What is the value for G? Giga. Tera giga. Times 10 power of what? Find it out by yourself. I already told you your calculator can help you. Find it out. The wire is fixed at one end. If you don't know how to find the prefix from your calculator, you capture your calculator and then you show me. I will tell you how to do. Because different model have different way to find out the prefix. One of the calculator cannot. It totally don't have. So you capture and then you show me. I will tell you how to find. The wire is fixed at one end. The force is applied to the other end. The force extension. So this one is X. Wire obey Hooke's law. Okay, what is the force? So E equals to FL over AX. So 360 times 10 power of what equals to the force. Want to find force. What is your length? 5.2. What is your area? Oh, you have to count area first. Pi d squared over 4. Let me check. Somebody capture your calculator to me already. Wesley sent to me. Let me have a look. Yeah, okay, Wesley, I teach you. You press 360. We want to find 360 giga, right? You press 360. Then on your left hand side, second button, OPTN. You press OPTN option. After you press the option, number 3 is engineer symbol. You press it. Inside got prefix. You find what is the number for G. Then you press the number, you press the equal. Then you will solve the answer. Wesley, you try. 开签 correct, 开签. Vashini correct. Pawal correct. Yes, dear actually is the same thing, but they test on you prefix. Do you know to convert? And then they test one more part. Calculate area by yourself. Calculate area by yourself. Wesley, do you able to press your calculator? Victor correct. Okay, good job. Okay, dear, here answer is B. The force that you get should be 391.3 Newton. So we will make it two significant figure 390. So which is B, answer B. Done? Any question? If no question, give me a response. We go to page number 4. Question number 3. Okay. Done, dear. Okay, next slide, dear. This one, challenging question. I guide you, dear. Okay, this one is an elastic cord of unstretched length. So unstretched length, this is original length L. This is original length. Cross-sectional area, this is your areal. And hold horizontally by two smooth pin at a distant X. Okay, so the cord obey Hooke's law. So we can using F equals to Kx. So it apply in the Young modulus. So F over X is applied. Okay, a lot of mass. So this one suspended here. Okay, suspended at here. Then the angle between the two sides middle is 60 degree. Okay, this one going down, this is the weight, right? Okay, we want to using the formula to calculate the Young modulus. So FL over AX. Okay, dear. This one, the force experienced by the spring. At here is the cord. So this one is the tension. Tension. This one, two cord is pulling up, right? It's pulling up. Object pointing downward weight, so the cord pulling upward. Okay, so at here we need to find what is this T. We need to find what is this T. If you are graduate from SPM Malaysia syllabus, this question not hard for you because we can resolve it. Okay, we resolve it here. Then this one resolve it. I want to know the upward force. Why? Because I know this overall system, they are equilibrium, they hanging. Hanging means that equilibrium. When the equilibrium, the upward force must be equal to downward force. Upward force equals to your weight. Right? Upward force equals to your weight. How many upward force? I got 2. One is from the left-hand side, the tension. Another one is from the tension on another side. So I got Ty1 and Ty2. But basically, Ty1 and Ty2 are the same. So I can just say that 2Ty equals to my weight. T resolve into vertical. T resolve into vertical, so I got 2 upward force, Ty. Okay, so how can I calculate Ty? Ty is 2, here, this one, T, resolve up, Ty. So this angle is actually 30 degree. So here is 30 degree. What is my Ty? My Ty should be T cos 30 degree. So 2T cos 30 degree equals to my weight. Weight is 0.4 times 9.81. So do you able to calculate the T? This tension is the force experienced by the string, okay, by the string called tension. So this actually is our force in our Young modulus formula. So you have to calculate the tension, put it into the force. Okay, then the length they already told you 16 cm, area already told you. So they're asking, oh, one more extension. How much is extend at the end? Okay, so can you see that? In overally, the length of the string is x times x times x. Sorry, not times. X plus x. In overally, it's already become 24 cm. How much is extend? Original is 16 cm. After we hang the loop, it become 24 cm. The overall length become 24. So what is your x? Do calculation. I already got you until here. Like for those, if you are graduate from O level, it might be a little bit challenging for you because this resolution is new topic for you. Okay, resolution is new topic for you. So because they are hanging that means balance. So upward force equals to downward force. We got two upward force. Now, boys and girls, you try and then you tell me what is your answer. Or any of you cannot understand about my explanation, you can also ask again. Prasan, very good. Prasan, correct. Can read. Okay, wait, Wesley, let me have a look for others. Vashini, correct. Kai Chen, correct. Manjo, no. Manjo, try again. Like dear. Wesley, here, we need to using this formula to find Young modulus, Wesley. We need to using this formula. Okay, this formula FL over AX. L is already given in this question, the length. Original length is 16 cm. It's already given. So L settle. Area also given, area settle. Okay, now we have to settle the force and X. Force actually is, what is the force experienced by the spring or string, or in this case is cord. That means that what is the force experienced by this? So when it hang, it will experience tension. This is the force in the cord. Okay, this is the force in the cord. We call it as tension. Actually, it's force. Okay, the name for the force in the cord we call it as tension. Okay, so because we hang the object, we hanging. Hanging means that the system is in balance. If in balance, then the upward force will equals to downward force. But initially, I only got angle tension. I don't have upward force. So I need to resolve it. Resolve it into y-axis. How I resolve it? Okay, this one here. Tension cos 30 degree. Because this 60 degree is for both. So I split it up. Going up is cos 30 degree. So this part, I find and resolve the tension in y component. So it will be T cos 30. So tension on left hand side, tension on right hand side, both will create an upward force. So I got 2 Ty. Ty1, Ty2. These two values are the same. Okay, 2 Ty. It will equals to the downward force W because system imbalance. It not moving or not moving, hanging. Okay, so after that, the weight is 0.4 times 9.8 mg. So 2 Ty is T cos 30. So 2 T cos 30. Actually, at here, your answer for this tension, you should able to get 2.265 Newton. This is the tension. Tension is the force 2.265. Okay, is the force. What is the length? 16 cm. 16 is actually 16 times 10 power of negative 2. Convert to meter. Okay, the area given in the question is 2 times 10 power of negative 6. Okay, until here, Wesley, until here, is it okay? Actually, the difficult part actually is this tension part. You are going to find the tension in the string. Okay, then the last one, extension. Extension, how much is extend for this cord? Initially, total length is 16 cm. After I hang the object, I become here x cm. Here x cm. Can you see that this is x cm? Of course, another side also XCM. So XCM plus XCM plus XCM actually in new length 24 cm. Original length 16 cm. So in between them, how much extension I get? So actually answer should be XCM. So it should be x times 10 power of negative 2. So the x actually is 24 cm minus 16 cm. So you get XCM. Where we get this 24 is because this triangle. XCM, XCM, XCM. Like Wesley? Vowel. Vowel correct. Like Wesley for this part. Manjo, let me have a look. Manjo, Manjo, Manjo. Manjo C. Manjo answer C. Like any of you, I know this question a bit challenging, especially if you are taking O level, not SPM. Okay, do you able to get the idea or which part you cannot get it? Can Okay, good job. It takes time for us to learn new things. It's okay. Like dear, if okay, then can I proceed to the number 4? Give me some response dear here. Okay, like dear, come here. A metal wire P obey Hooke's law. Okay. Another wire Q is made from a wire that has double twice the Young modulus. So this one is 2E. 2E. So just now P is E. Okay. So this one is for Q. Q is 2E. So P is only E. Then wire Q has same volume, V volume. Okay. As wire P. Q equals to the P, but has a double cross-sectional area of wire P. Area for Q actually is double for area for P. Okay. Okay, now I got one question. Because now we're talking about this is about the what? Young modulus FL over AX, right? So area. Yes. Length. If these two wires having same volume, what happened to the length of wire Q? What happened to the length of wire Q? What do you think? The wire Q will be longer, double the length, or actually, yeah, half of the length. Am I right? So volume are the same since the area already double up. Then your length will be half of it, right? So at here, from this sentence, I can get another third information from this. I can take third information. My length for the Q actually will become half of it. Am I right, dear? Do you get the idea? Same volume. If you double up, then your length will be shorter. Okay. Then if your area is half of it, then you will be longer. At the end, you can create a same volume. Get it? Is it okay? Okay, the wire are extended by equal force. So this one, the F are the same. Okay, the extend with the same force. Stand and explain how the extension. Oh, they want to find about this. Okay, they want to find about X. So can I rearrange this formula? X equals to the FL over EA. Am I right? I want to compare about their extension. So from this Young modulus, I rearrange the formula. Okay. Now we are going to look at the Q. Q right now has double E. Okay, double 2E. So at here, I want to know about Q. So force still the same. Length weight, so this one is 2E. Because this one, okay, is 2E. Okay, 2E. Then area for the Q is 2A. Okay, 2A. So this one area is 2A. The length is half of it, L over 2. Until here, any question, dear? If no question, can you give me response so that I continue proceed? Can ah? Can ah? I just interpret from the sentence, find out what is your Q, okay? So I find out that the Q actually have a 2E double, okay, 2E. The area also double, so 2A. Since they told you same volume, so if your area already double, then your length must be half of it. So from here, actually, I can calculate and I will get 1 over 8 FL over AE. That means that my extension actually will reduce 1 over 8 times. Then you compare with your extension of wire P. Your wire P is FL over AX. But your extension for wire Q will become 1 over 8 of it. Okay? So at here, I write the answer. Here, 3 marks. They expected to see that about the length. So you have to mentioning the length of Q is half the length of P, like this 1 mark. First information you have to know about this so that you can do comparison for the extension, okay? So extension is proportional. Extension is proportional to length. Because the force is constant, okay? Force is constant. So if length increase, your extension will increase, okay? Then inversely proportional to area. That means that here, you see, area greater than extension will be decreased. This relationship, one high, one low, this relationship called inversely proportional. Okay, then after that, and also not only inversely proportional to area, but also E, Young modulus. Okay, so this is another second mark. You know their relationship, okay? You know the extension, what will be affecting the extension. Okay, you understand what will be affecting the extension and how they affecting. Is it increase, increase? Is it increase, decrease? Then next, the last one is extension of Q is actually 1 over 8 times of extension of P. Third mark. Okay, not easy, but step by step we think about that, we still able to solve it. Slow, one step by one step. Actually, it's mathematics, you see. Actually, what we did is about mathematics. That's why I told you in A level, your mathematics must be good. Okay, Jore asking why the length is half. Jore is because they told us that this volume are the same. This volume are the same. So your cross-sectional area double. When your cross-sectional area, okay, you look at this. This one I already draw a lot here. I give you space at here. Let's say this is the area, okay? Area 1, which is like let me think 2. Okay, let's say it's 2 meters square lah. I just simply give a value. Then this one is 5. Okay, what is the volume? Volume will be the area times the length. Am I right? So it will be 2 times 5. So it's actually 10 meter cube. Okay, Jory? This one okay? So now I told you that I have another wire. It's double up the cross-sectional area. So now this one double up. It becomes 4 meters square. Double up. But do you think that you're still having the 5 meter length to get the 10 meter square? The volume at here is still 10 meters cube. But here, my area is 4. 4 times the length, I get 10. So 10 divided by 4, actually you get 2.5. Am I right? You're right here. You will get 2.5 meter. That means that this one, the length, it will become 2.5 meter. My boys and girls, this one in more detail to tell you. Okay? Got it. Yes, good job. Okay, so when the volume are the same, area double up, then your length have to half of it. That's why here we do substitution, length is half of it. For the Q, area double up, but length half of it. Like any others question, boys and girls? Any of you facing problems? Okay, Farewell, okay. How about others? If no question, I want to go to page number 5. We do one more question before we end our lesson today. Hi. Okay. Okay, good job, dear. Let go. We go to one more question. Okay, two wire X and Y with equal unstressed length. So this is the unstressed length. So this is original length L. Suspended from the fixed point that are at the same horizontal level. The lower end of the wire are attached to the beam. We ignore the mass, okay? So we don't give any extra weight. The beam is horizontal and equilibrium. That means hanging, okay, horizontal. The wire X is made from the metal with the Young modulus. Okay, so this one Young modulus for X, EX. Okay, the wire Y made from different metal, so it will having different Young modulus. A lot of acting Newton. So this one is your force. Am I right? This is your force acting Newton. But dear, this force acting Newton, as I told you, you imagine you are the boy, you are the one standing here. There is another boy standing here holding the object together. Will you experience acting Newton? No, the acting Newton will be shared out by you, right? Shared out by both of you. So each of them actually you will receive 9 Newton only. You share out the weight already. Okay, holding together, share out. Okay, so at here what information we still have? Cause the wire to extend 0.4 mm. So this one is extension. Determine the cross-sectional area for wire X. Okay, wire X. Now I'm only talking about wire X, so you don't bother about this. Okay, but I know lah, it experienced 9 Newton. So now 9 Newton, we're talking about this part. For the wire X, because they're already giving us the Young modulus, so E equals to FL over AX. For our X metal wire X, okay, here 1.9 times 10 power of 9. This is given by the question. What is the force experienced by the wire X? Wire X only. Acting Newton share out. So your 9 Newton, your wire X only receive 9 Newton. Only 9 Newton, not acting. Don't apply acting. It's 9 Newton. What is the original length? So here 0.84. 0.84. What is the area? Is there mentioning about the area? Oh, we are finding the area. Finding the area. What is your extension? Both wire extend 0.47. That means here 0.47, 0.47. So I look at this, we only applying 0.47 times 10 power of negative 3. Okay, let me check. A lot of you message me already. Okay, Farewell, correct. So there, at the end, A equals to 8.5 times 10 power of negative 6 meters square. So boys and girls, for me, actually this question, what is the difficulty part? Okay, what is the difficulty part? Actually is this. They test on you. Do you know that wire X only experience 9 Newton? Okay, this is the thing. Okay, let me have a look. Kaichen, correct. So dear, no question for this one, right? Actually, it's testing on you, practice on you. Do you know it's 9 Newton? Okay, now we look at the last part. Okay, here. Wire Y has a greater diameter. Okay, greater diameter. That means that your cross-sectional area will be higher lah. Am I right? Okay, your area will be higher, greater area. Explain without calculation, we no need to do calculation, whether the Young modulus E from which wire y is less or same or greater than the 1.9. 1.9 is in x lah, okay, from wire x. So E is actually FL over AX. Okay, what do you think, dear? Type your answer. Finish this question, we can relax. Next week, no lesson, dear. Next week, no lesson. I'm so sorry about that, but I cannot avoid from the school activity. So in October, we will have 5 lessons, continuous. Okay, like dear. Correct, Farewell. 2 marks, huh? Wesley, correct. Okay, dear, here they give 2 marks. How they allocate the mark? Washini, correct. Okay, final answer for these are actually our Young modulus for y, it will be decreased, lesser. It's because our area is greater. Okay, so for this answer scheme, actually they want you to mentioning about F, L, and X are the same for both of them, for both wire. Okay, 1 mark. Then area is greater for y. So Young modulus for y is less than 1.9 times 10 power of negative power of 9 Pascal. Okay, so this one is another 1 mark. So boys and girls, here they want you telling us that others variable is constant. Now your Young modulus affected by area. Area greater, so your Young modulus will be less than the E. Okay, any question there? No,